So yes, so today we're very happy to have a hub seminar given by Daniel Platt, who's an ICRF, so that's Imperial College Research Fellow. Very nice, senior postdoc position for 4 years at Imperial, and Daniel works on using sort of machine learning to aid, AI for mathematics, and that's what he's going to talk to us about today, about numerically verified proofs, and we're very excited to hear about that.
All right. Thank you very much for the friendly introduction. Yep. So this talk is about numerically verified proofs, and my main application is a proof in geometric analysis. So I'll spend some time on this, but I know many in the audience care a lot about machine learning and maybe topological data analysis, so I snuck in some other applications of these numerically verified proofs. And in fact, here's what I'll talk to you about. I'll start, so this is very example-based. I'll start with a classical problem about root enclosure. There you see this one principle that all of this stuff is based on. Then comes my favorite application, this Nirenberg problem, the geometric analysis one. And then depending how much time we have, I talk about 1 or 3 more applications which are taken from the research interests of various hub members. So, but we can stop whenever we get bored. I don't need to get through all of this. And also, you are strongly encouraged to interject and ask questions or make comments. This would be greatly welcome, because if it's just me talking, I probably don't have enough to fill an hour. Good. Let's start with the baby example, root enclosure. Let's pretend we want to find zeros of this function here, curly f, which is x squared minus 1. Now, we went to high school, so we know that this has a solution. It has even 2, plus 1 and minus 1. But let's pretend we don't know this. What I'm about to tell you works for all polynomials, and there can be some really complicated polynomials where you might not just be able to write down a solution. And one thing we also learned in high school is you can compute an approximate solution, which I'll always write x approx, also on the next slides. And then you can use this Newton iteration scheme. So what Newton iteration does is you start at your approximate x approx solution, and then you take the tangent. You take the tangent to your function at the point and see where it intersects the x-axis. So this gives you this x star. And hopefully, if things are nice, then x star is a better approximate solution than x approx. And sometimes it converges, sometimes it doesn't. And what all of these slides will be using is one sufficient criterion for this iteration scheme to converge. Yep, so what will happen is we never actually do the iteration. We'll just prove that this sufficient criterion is satisfied. So we know if we ran the iteration, it would find a genuine solution. And this is the existence proof. That's how you prove existence of solutions to these equations. The theorem is there on the bottom of the slide. It will come up soon. But what you first have to do is you have to do some computation. That's the numerically assisted part here. So let's say you run your cluster for a day or something, and let it come up with the best numerical approximation it can to solve this equation. So for example, I let my computer run for a day, and it computed 0.999, which is pretty good, because secretly we know 1 is a solution. But let's pretend we live in this world where we don't know this. Then how this works is you Taylor expand your target function, you Taylor expand your curly f. Here I did this for your convenience. This f of x approx, that's the 0th order term, and then there's one linear term, and then there are several higher order terms. And in what we're about to do, this 0th order term is called the residual. And I always use it's also called the error, and I use this curly e letter. And if you had been super lucky and your computer computed an exact solution for you, then the error would be 0 and you could stop right there. Nothing else you have to do. But the whole point is that this is for situations where your computer doesn't give you an exact zero, it just gives you some approximate solution. And so, for example, here, if you plug in this 0.999 into the equation above, that's why you get 0.002. And here comes this sufficient criterion for the Newton iteration to converge. So this is what it looks like. It's a long theorem, but it will appear on basically every slide, so you'll see it many times today. And what that says is you need three estimates. You need this estimate for the residual, so a bound for the residual called C1. You need the bound for the linearized operator, which is C2. And then you need the bound, which looks a bit funny here. So yeah, something involving the higher order terms. And this estimate should give you a C3. So here for the linear guy, this is complete overkill for this polynomial example. Later, this notation will actually be necessary, but here I could have written it much simpler. What this means is I view the linearization as a linear operator and then compute its inverse, and then I take its operator norm. In this case, it's all a bit ridiculous because this is all one-dimensional, so L is just a number, and the inverse is just the reciprocal of this number. And then this theorem tells you that if these bunch of inequalities are satisfied, so two inequalities are satisfied, then there exists a solution of your equation f equals 0. So then there exists a true solution. And before we move on, let's look at these two inequalities that should be satisfied. So what do they really mean? C2 and C3, they are kind of, they are what they are. They are given in nature. You can't really change them. That's a part of the problem. So the second inequality, this guy here, the 2, C2, C3, R, tells you you need to choose the R very small to absorb these other constants. Now, the second inequality may tempt you to take R equals to 0. So let's pretend we do this. But then you're a bit in trouble with the first inequality here, because then you get C2 times C1 less than or equal to 0. So you can't literally take R equals to 0, but you wanted to take it pretty small. And the first inequality then here, the C1, that's the only thing you can really compute and improve. So if you let your computer run longer, you can make the residual smaller, so you can make the C1 smaller. So that's the only handle you have. Compute better, make the C1 smaller, and then you can get away with a very small R. And so here in this case, it's actually all fantastic. For this particular approximate solution that I told you, we have C1 equals to 0.02. That's literally written up here. And if you go through the motions and compute the derivative and take the reciprocal, you get roughly 0.5. C3, this funny estimate, we'll see a bit more detail how this is computed later, is 1. And then these two inequalities hold for R equal, for this particular R value here.
So you said like the C2 and C3 are basically given from my problem. So that, of course, they depend on the function f, but also do they also basically depend on where I want to basically do this machinery?
Yeah, the question was, so I repeat for the people online, do C2 and C3 depend on where you actually do this thing? And the answer is yes, I lied to you. I pretended these are just God-given numbers, but actually they depend on your approximate solution. However, they depend in a really mild way. So if you change this from 0.999 to 0.9999, these C2 and C3 will basically not change. You can kind of see this, well, or just take my word for it. Sure. So you are correct, but also I'm also correct. That's right. That's the crazy thing. You only need to satisfy it. You only need to check E and L at one single point. The only global thing is this N estimate. Absolute magic, yeah. Yeah, other questions or comments before I move on? Does it say anything about the uniqueness? It does. I didn't say this because it didn't fit into the last line, the word unique, but there's actually a unique V in this ball which solves this equation. So it says the local uniqueness. And you immediately know it can only be local because, for example, in this example here, x squared minus 1, this theorem will tell you there is a unique solution near 0.999, but it totally misses the -1 solution. Yeah.
Hello.
Hello. Are you
Yes.
on the call? Oh no.
It's just this is the talk I wanted to follow, but it's okay.
Yeah. Okay. So let's crack on. Now we've graduated from the baby example. Now we go to our exciting example, the geometric PDE, the Nirenberg problem. And I won't spend super much time on it to explain why the problem is so exciting. I'll talk more about the analysis, but just to get you hyped up a little bit, here's one slide. The Nirenberg problem asks which functions k on the sphere are the curvature of some metric that's pointwise conformal to the round metric. Okay, if you know what this means, that's great. If not, it doesn't really matter. I'll translate it into a PDE in 1 second, and then you don't need to care about conformal and all this stuff. And there's a recent preprint, not by me, titled Machine Learning Approach to the Nirenberg Problem. And what they did there was experimental mathematics. They took many, many functions, k, and tried to solve the equation, try to solve this conformality equation. And among other things, they printed this one table here, where each column stands for one k that they tried. And the vertical axis is the loss that their neural network produced. And the green ones are the ones where there's some theorem that guarantees you, yes, there must exist a solution. The red ones are the ones where there is some theorem that guarantees you there cannot be a solution. And then there are the gray ones, which are the mystery ones, where you don't know if there is a solution or not. And if you have very good eyes, you can see this SH32 here. This will appear later on. And SH32 is one of the mystery ones. Correct.
They still found a loss function with loss 10 to the -6.
That's also correct, yes. It's not great. It could be worse. So at least the negative ones and the positive examples are separated by something. If you do really bad quadrature, for example, like you have very few test points, it could happen that you get the loss of a red one below the loss of a green one. At least this doesn't happen. But yeah, the margin between red and green is pretty thin. Yeah. Good. Now, this was the geometry formulation of this question, but if you like analysis, then you immediately write it like this. You ask, does this partial differential equation have a solution? 1 minus Laplace u minus k e to the 2u equals 0. So we're looking for a solution u on S2. And then maybe if you're very adventurous, you could also ask, is this unique? Does it have any symmetries? What does it look like? Many interesting questions you could ask. Now, the way this is solved using, okay, first I need to state the statement of exactly what it was that I proved. And for this, I write down these real spherical harmonics. So they are indexed by two indices, L and M. And there are restrictions of certain polynomials to the sphere, and they look like this. We have one spherical harmonic of degree 0, and then we have 3 spherical harmonics of degree 1. So you can see they have one of these white regions here. Yep. And then we have 5 of degree 2, and so on and so forth. Then I got bored of drawing them, but you can go up to higher and higher degree. And y 3,2, that's the SH 3,2 from the previous slide. That's one of the mystery spherical harmonics. We don't know, well, now we do, but we didn't know if this Nirenberg problem has a solution for this particular function. And okay, a thing you may care about is that it has some symmetry. It has a discrete symmetry, which is this group here. It's plotted below. So this picture here on the left, this shows the this spherical harmonic, and it has all the planes of symmetry plotted for you. And if you count the number of symmetries, you should end up at 24. And what the theorem then says is, yes, there is a solution for this particular prescribed curvature. And there is not only one, but there are actually 5 different solutions to this equation. One has the symmetry group of the problem that you started with, and the other 4 have less symmetry. So here on the bottom right 2 pictures, those are the 2 types of solution. One has the full symmetry and the other one does not. And if you reflect the middle ones across one of the planes that's not a plane of symmetry, then you get these 4 different solutions. Good. Any questions about the statement? No. Then I will hit you with the proof of this statement. So first comes the overview slide. So this is very heavy analysis, and I guess the next 2 slides as well, and then it gets a bit more, then it gets less analytic. So as a reminder, that's the equation we want to solve here, right at the top. And if you want to solve a PDE, the first thing you have to do is you have to choose some function space in which you want to solve the PDE. And you can open a textbook, there are many standard choices. I took the most standard of standard choices called the L2 norm here. So just well, we all know this, the integral of the function squared. And then the Sobolev norm is the L2 norm of the function and its derivative. And then I always use these symbols L2 and H2 for the function spaces, and they will appear a few times. So the proof overview is exactly the same as in the toy example. First, we compute an approximate solution, U0, now it's called U0. And what that means is you want that the residual is small, namely small in this norm that I defined upstairs here. And then now this is the part that's actually complicated for PDEs. That's what's different from the polynomial case. Now we look at the linearized operator. And it's a bit messed up because this F is a map between infinite dimensional spaces. So if you don't do this every day, maybe it's a bit weird to wrap your head around what this linearization is. But it turns out in many interesting PDEs, it's like the Laplace operator or something like the Laplace operator. So here I wrote down for you what it is. It's the Laplace operator plus some other junk term. And these function spaces were exactly chosen in such a way that what I wrote here is true. So it goes from H2 to L2 because this operator takes 2 derivatives here. Yep, and then we need to estimate this. So this will be the next step. And then there are these nonlinear terms, which in this case, yeah, again, I wrote it down for you. It's just the full equation minus the linearized terms. This gives you the these higher order terms. And so this is roughly, again, this is precisely our Taylor expansion of the function f again. And this Newton-Kantorowicz sufficient criterion theorem in this case looks like this. It is exactly what's on the previous slide, except for one difference that the eagle-eyed among you may have spotted. The norms are now different. So E is no longer a number, so I can't just take its absolute value. Now I need to say what norm. And obviously I take one of these norms here because that's why I defined them. And that's what the theorem now says. Yep, so these 3 quantities, C1, C2, C3 are the 3 guys we'll have to compute. And that's what we do now. So the first one is the residual E. Again, on top for you, the equation we're solving and the Newton-Kantorowicz theorem. And you first start by computing some approximate solution to your equation. And it really does not matter at all where it comes from. It could come from a neural network. It could also come from something else. Because unfortunately, I'm a bad salesperson. I didn't use a neural network. I used a spectral solver to approximately solve this equation. but it could have come from a neural network. I just didn't think carefully. And the first thing you have to do then is to prove some upper bound for your function. And what we do in machine learning is always just evaluate the function at many points, but this doesn't really cut it here, because how do you know it's not going to explode exactly between two of these collocation points that you chose? So we need to do a bit better here than just evaluating at many points. We need to prove some rigorous upper bound. And one way you can do it is you just use the triangle inequality. If we want the norm of u0, and u0 is such a sum here, you immediately get this inequality here. And the ALM, those are the numbers that your approximate solver gave you. These are some numbers in my computer. And the YLM, these are the spherical harmonics. I can just open the book and see what are their L infinity norms. And then you get some estimate. And I say it's 1.58 here. And this is not sharp at all, but it doesn't matter, as you'll see. We just need some bound. Now, this is the first place where I told you, or actually, again, I told you a small lie here. And that is, if you do literally what's written here, you don't get 1.58, you get a bigger number, which would still be fine, but it just makes the computation time from 17 hours to like 17 weeks or something like this. So there is a trick how you get to this nice number 1.58 that I employed, which is called the Lipschitz method. But it's not the point today. And if you have a good computer, you really don't need to care. The next thing then is to approximate this exponential in this equation by a polynomial, and you'll see why in a second. So let's take p equals to 50 and let exp p be the degree 50 Taylor polynomial of exp. What you then have is you can compare exp with exp p, and you find that the difference is super small. If you write down the Taylor polynomial of exp, then you'll find that this difference has a p plus 1 factorial in the denominator, so this is going to be a very small number. And then everything is in place to estimate the residual, to give a really honest-to-God bound for the residual, and this is it. As a reminder, we want to have the L2 norm here of this guy, and we split this in two parts. First, we pretend that our equation literally is exp p, not exp. So what's written here is exactly the equation from above, just written with exp p. And then there's this error term. We made an error because we were a bit dishonest about our exp, and we get this plus from the triangle inequality. And the second summand is super duper small, thanks to the previous line. That was this error estimate. And the first summand could be small, could be big. This is exactly the thing that should be small if your solver did a good job. So there's a priori no guarantee that you can get this to be small, because you don't know that your equation has a solution before you start. But if your solver does a good job, then this will be small. And in my case, the two terms together were 10 to the minus 8, roughly. And yeah, okay, maybe that suffices. Good. This is the first step. Now comes the hardest step. Now comes bounding the linearized operator. So again, here the equation we want to solve, curly f, and L is this linearized operator. And the estimate that we want looks like this. Previously, I wrote this in terms of the operator norm of L, but if you remind yourself of the definition of operator norm, it's actually equivalent to this estimate here. U less than or equal to C times L, and we want this constant C explicit. And roughly speaking, this constant is 1 over lambda 1, which is the smallest eigenvalue of your linearized operator. So there's something I sweep under the rug here. But going from the smallest eigenvalue to this constant C here is pretty straightforward. So I won't talk about it, but I will talk about it in a bit more detail, how to get this smallest eigenvalue. And there are two approaches you could take, and I'll tell you about one of them. The one that worked well in this case is that you split your function space on which you work into two parts, into a low degree part and a high degree part. So L33 doesn't particularly matter what this number is, but then here we have our low degree part and we have our high degree part, where degree means, well, basically, yeah, the spherical harmonics are a restriction of a degree what polynomial. That's what their degree is. And thanks to this splitting then, we can write our linearized operator in this block matrix form. So A goes from low degree to low degree, D goes from high degree to high degree, and C does whatever. And now we can estimate all these blocks individually. So the cool thing, and that's the whole point of doing the splitting and so on, is that now A is a finite dimensional matrix. I haven't told you what the dimension of this space is. I think it's around 500 or something. But whatever it may be, it's finite dimensional. And so what you're doing then is to compute the smallest eigenvalue of a 500 by 500 matrix, which is just some finite dimensional computation. And I claim the smallest eigenvalue is 2.04. Now I make it seem a bit easier than it is because you can't really invert. If you want to do rigorous numerics, you can't invert such a big matrix. It would take too long. So there's some tricky linear algebra, but I didn't have to invent this. People have invented this before me. So there are now ways so that you just need to write in Python, invert this matrix, and it does it for you. Good, that's the finite dimensional part. And then there is this infinite dimensional part. So this high dimensional block is still an infinite dimensional vector space. So this is not just a matrix. So you cannot just go into Python and write invert this matrix. It doesn't make any sense. But luckily, we're in this high degree, on this high degree space. And then we can just give a pen and paper proof of some bound that we need. And this is what the proof looks like. Here, D of U. First, I plugged in the equation for you. So this is the Laplace operator again. And this is this 2 times k part. Yeah, so here this L is written up there. And now the thing is, because we're on a high degree space, our degree was at least L. You get a number L squared here, which is pretty big. It's going to be like 1,000 or something. And here, on the other hand, this is just some junk times U, and you just compute an upper bound for the junk, which will be some constant here, C. And what you end up with is some estimate, like roughly 1,000 minus some junk constant, and you get roughly 1,000 still. If you work it out, it's true. You really get 10 to the 3 here. Good. And then the last one for C. Let's pretend it's 0. Just for the nerds, I'll say one word, and that is, if you make your L very large, you can get this number, which is 10 to the 3 here, as big as you want. And then the C doesn't really matter anymore. If you imagine you have a block matrix, A is whatever it is, D has some huge eigenvalue bound, it doesn't really matter what C is anymore. So that's roughly how the argument goes there. But let's pretend C is 0. Then we're literally computing the smallest eigenvalue of a block matrix. And the smallest eigenvalue in this case would be 2.04. And then I said, oh, it's straightforward to go from the lambda 1 to the C. And if you do this straightforward thing, you get 50.55. Okay, so this was the toughest slide, and I omitted a bunch of stuff, so it will get better. But any comments or questions on this part here, the linearized part? Okay, very good. If not, let's crack on. So now you're basically out of the woods. The rest is pretty smooth sailing. Now comes the higher order terms estimate, which looks complicated, but it's very easy to do, really. Let's pretend the higher order terms are u squared. In reality, they were something with an exponential, but it doesn't change anything. It just makes it more annoying to write down. So let us pretend this. And here, as a reminder for you, is the Newton-Kantorowicz theorem. So here is this funny looking estimate that we want to prove for n, for the higher order terms. And I'll make this, literally this estimate, appear in front of your eyes for you right now. So I start with the thing on the left-hand side here. And because we pretended it's u squared, I can use the third binomial formula. u1 squared minus u2 squared is what's written here. u1 plus u2 times u1 minus u2. And then you use the, what do you use? You just pull out the maximum of one of these functions here, or Hölder inequality if you like a fancy name. And then there's one complicated step where you have to convert this infinity norm here into an H2 norm. So there you have to open a book again and look at find the correct estimate, and it's called Sobolev embedding theorem, and it tells you that this step here is true, and it also tells you what this constant here is. And now you've really done it all, and just to drive this point home. So it seems we did a bunch of random steps, but actually we arrived literally at what we wanted. Okay, even better, there's L2 written here. We wanted H2, but H2 is even bigger than L2, so we proved something even sharper. The C3 is the geometric constant, isometric, isoperimetric inequality. Yeah, so the geometric data enters there, but it's even easier than the isoperimetric constant. It's like the Sobolev embedding constant is, it depends in a very mild way on some curvature or something. Yeah, but yeah, so that's right. So geometric data does enter here. And for S2, it is very easy. You just open a textbook and you see the constant. If you are on some crazier manifold, you would have to work a little bit here. Right. In this case, it does not change with the approximate solution that I constructed, because just how the problem is set up, you always start with a round metric on S2. And this is a constant for the round metric. So this is a particularly simple problem. Normally you're right. Yeah, if your approximate solution dictates the geometry of the space that you're on, then this constant will change. But to go back to Camilo's question from slide 1, if you refine your approximate solution, this changes in a very mild way. So if you find yourself in the situation that you compute a better solution and your C3 jumps like crazy, that's an indication that maybe there is no solution. Or at least it's an indication that this scheme will not work. Yep, and now this is the home run here. So we computed C1, 2, 3, and if you, well, I didn't tell you what C3 is, so you cannot do the math on a sheet of paper right now. But if you take my word for it and you take R equals to this number here, 3.1 times 10 to the minus 4, then these two inequalities in the Newton-Kantorowicz theorem will be satisfied. So you know that a solution exists. And you know even more, because the last sentence here says V in BR, you know that the existing solution is super duper close to your approximate solution. So that's how you know that there are really different solutions, because you do this 5 times for the 5 different approximate solutions, and then you're done. Good. No one asked, but I have an emergency slide at the end, if we have time to kill, about how you prove the symmetry statement. So the theorem that I made also contains a statement about the symmetry of these solutions, and I haven't said anything about this yet. And I won't for now. Good. Okay, so this was the hard stuff. This was the Nirenberg problem. So what comes now is like some examples, maybe related, in some sense related to AI or computational topology or something like this. And the first one is actually serious, and I will need this in my research. And the other ones is just to show you could really choose any topic and do a numerically verified proof in it. So if you're ever looking for a student project to suggest to a student and look no further, just take one thing that you're working on anyway, choose a small example and ask them to numerically verify this. First example of the second batch, bottlenecks of submanifolds. Let's say, just for concreteness, we have a curve gamma, which is a curve in R2, but this is completely general. The domain can be any dimension. The embedding space can be any dimension. It must be Euclidean space. Then 2 points on this curve are called a bottleneck if they are a critical point for the distance function. So for example, in this picture here, this dotted red line is a bottleneck. Because these 2 points are actually a minimum for the distance function, a global minimum even, but we wouldn't need this. There's another bottleneck the other way around, which is a global maximum for the distance function. But also if it's a saddle point or something, we still call this a bottleneck. And so this is the equation for this ellipse that I drew here. Gamma of t, some stuff like rotated by 20 degrees. And this is what I call the distance function. So d of s comma t, gamma of t minus gamma of s, the Euclidean norm squared, makes it a bit easier to talk about derivatives and so on. And so that's what we want to find critical points of. We want to find critical points of this function d. So our target function is this curly f. Curly f equals to nabla d. We want to find zeros of curly f. So it's exactly the same notation as on the previous slides. And the approach is exactly the same. Approximate solution, linearization, higher order terms. So let's start with the approximate solution. You let your cluster, your university cluster run for a week, and your computer comes back and tells you it found this approximate solution here, which is roughly, I think, pi over 2, 3 pi over 2. But you don't know this, it just gives you some float numbers. And what you can then do is you can compute the residual. You just plug this approximate solution into your function f, and what you'll find is that the norm is roughly 10 to the minus 3. Okay, let's see if this is good enough to do our Newton-Kantorovich. Fingers crossed. Let's compute the linearization of this equation. Slightly messed up example because our curly f is already the derivative of something. So curly L will now be the second derivative of f. So it's the Hessian of this distance function if you write it all out carefully. And right, this is a 2x2 matrix. So now you actually need to decide what matrix norm do you want to take. So 2x2 matrix, you can invert the 2x2 matrix, and I took this infinity matrix norm here. It doesn't really matter, but this is a choice you have to make at some point. And I computed it for your benefit. It's 0.5 roughly. And then there is this last estimate here, this nonlinear estimate. And again, take my word for it, it's super easy. So that's why I didn't write it down. It's super easy, but a bit confusing to write down. So it is 56 is what you get here in this case. And that means we've computed our 3 numbers now, our C1, C2, C3. Does there exist a little r which satisfies the 2 inequalities? And the answer is yes. If you take r equals to 1.1 times 10 to the minus 3, you can make these 2 inequalities true. So what you've done with all of this is to prove that there exists a genuine bottleneck near your approximate solution. Good. Questions, comments about this example here? Yep.
Question.
Yep.
Is it true from the theorem constants? Does it tell you how far you are from a natural solution once you decide to apply the iterative method?
I'm not sure I understand the question. So if I go back, if I flash the theorem here for you.
Yeah, so say I start.
I think the answer is yes, that V is in this ball of a very small radius.
Yeah.
So you know that your genuine solution, which is U0 plus V, is at most V away from your approximate solution U0. This is the result of the whole Newton iteration. This is not just one step.
But so you're guaranteeing that the Newton iteration will converge?
Yes.
Right?
Yes.
So I want to know how fast it will converge.
Okay, I see. So you ask how fast will the Newton iteration converge? And you can extract this from these two constants. Yes, you can do that. Yep. Yep. I don't know exactly how you must combine them, but it's possible. Mm-hmm. Okay, very nice. Bottlenecks of submanifolds. Then another thing you might be interested to do if you're in the Erlangen AI Hub is to look at diffusion geometries. So this reference here is Yolo Jones's paper where this, I guess this is an introduction to diffusion geometry. So there you can read up all these definitions. I don't think I can accept any questions about diffusion geometry because what I know basically fits on this slide. So you can ask, but I'm not sure I'll be able to answer. But the point is, you start with some point cloud in Euclidean space or somewhere else, but let's stick with Euclidean space, 100 points here. And then you can define lots of stuff from manifolds on this point cloud. So you can define vector fields, K-forms, and this Laplace operator, for example, if you want. And this is what this Laplace operator looks like. I won't read it all out, but this Kij here is called the Gaussian kernel, and then you do a bunch of stuff, and you end up with a self-adjoint operator, delta. And the point is that if you were sampling these points from a manifold, then these discrete objects converge to the smooth objects. So in a very complicated sense, this discrete Laplace operator converges to the smooth Laplace operator on the manifold that you sampled from, but it's really messed up to write down the precise estimate, which explains in which sense this is true. And as a toy problem, let's pretend we want to find a Dirichlet eigenfunction. So some function f, which satisfies this eigenfunction equation, delta f minus lambda f equals 0. And let's also normalize this to have unit norm, because you could multiply it by some constant and it would still be an eigenfunction, but this messes up the analysis at one point that I will try to remember, point out to you. Okay, so let's say you set your mind to solve this problem. How you do it is, again, the same 3 steps as always. First, you compute an approximate solution. So what that means in this case is you have to compute the approximate function f and the approximate eigenvalue lambda. And I did this for you, and it came out that lambda is 0.1 roughly, and the function looks like this. So I demanded it has this Dirichlet this Dirichlet boundary condition. I demanded it's 0 on the leftmost point and 0 on the rightmost point. But then I numerically let it solve this eigenvalue equation for this delta here. And that's what came out. So it looks like the thing, it looks like a sine curve, which is what you expect from classical analysis. But now it's actually taken into account that this is not literally an interval, but these points differ from the interval in this annoying Gaussian way. Okay, very good. This is our approximate solution, and we compute its residual as always. And so here's our eigenvalue equation up there. So I just plug in all this approximate stuff. And because our solver did a good job, this is a small number. This is 0.001. And that's and just to repeat this again, this is the one thing where you actually have leverage. If I computed more, I could get this number down. All the other constants, I can't really do much about them. The linearized operator is, in this case, it's a bit like in the Nirenberg problem. It's the Laplacian plus some junk stuff. And if you do it, so now actually this is a matrix again, because functions f, they're just values at these 100 points. So the Laplace operator is a matrix that takes 100-dimensional vectors to 100-dimensional vectors. This linearized operator likewise takes vectors to vectors. So now we are literally inverting a 100 times 100 matrix again. And here I didn't write down what matrix norm this is. And this is not good. It's actually very important for the problem. If you want to prove something, I took the Euclidean operator norm, but maybe it doesn't matter so much for this slide here. And it turns out this is roughly 1. And then again, I refuse to show the proof for this. It's a nonlinear estimate, but I claim it's easy. In this case, it's roughly 2. Yeah. And I should also say, you really don't need this to be sharp. So I think there will be one more example where I'm pretty lazy about computing a good bound here. If this was not 2, but 2,000 or 2 million, it really would be no issue at all. It just would mean you need to work a bit harder for your approximate solution. But I mean, here all these numbers are super benign, C1, C2, C3, and it's super easy to find a little radius R, which makes all of this true. So yeah, so the conclusion is, after all is done and dusted, that there exists a genuine eigenvalue near this lambda approx. And when I say near, I can actually exactly specify how near it is. And you know, even more than this, you know that the true eigenfunction is near your approximate eigenfunction. But maybe I only care about the eigenvalue. Okay, so far so good. Then let's jump to the last example. We've almost made it. Last example, point clouds for given barcodes. So I know there are many persistent homology fans in the audience. If you haven't seen persistent homology, this is not very useful for you. But the point is, given a bunch of points in Rn, you would like to compute the homology of these points, but that doesn't make sense because that would just depend on the number of points. So what you're doing is you choose little balls around your points, make them grow, and compute the homology of this growing complex as you vary the parameter. And what you end up with is a barcode like this here, which tells you what is the homology for each value of your growing parameter. So for example, for this what's drawn here, like a medium large parameter, we will be somewhere here in this region where we have one connected component and we have one non-collapsible circle. That's why there are 2 bars, which are pretty long. And I mean, this is a huge research area. I'm not making any attempt to give any overview over it. I'm just saying a question that people have been interested in is, given a barcode, is there a point cloud X which produces this barcode? Simple yes or no answer, or yes or no question. And what we also have is good numerical approaches that, given a barcode, it comes up with some point cloud X approx, such that the barcode of X approx is roughly the barcode that you started with. And I'll be slightly more precise about what this approximately equal here means. In fact, right now, I will be more precise about it. So to make this precise, we need to fix some neighborhood in this space of barcodes of our barcode B and identify this with some Euclidean set. And you can imagine the parameters, the Euclidean parameters exactly parameterize the start and end points of your barcodes. So this is one way how you can identify this space of barcodes with a Euclidean subset. And this is not my invention. This is, well, I've seen it in this paper, but maybe this is a classical thing also. Good. Then we also have to identify our domain with some Euclidean set here. And so our domain is the configuration space of point clouds. And so let's say we have L points, then this dimension of the configuration space is 3L, because you can move around every point in 3 directions. And our approximate solution point cloud can be identified with a point in this space here. And let's call V a neighborhood of this X approx. And the point of this is that now our target function curly f, which is this barcode function here. So barcode minus the B that we are targeting. Now is a space between Euclidean spaces. So from V to U, which are subsets of Euclidean space. And just as before, we want to find a 0 of this function curly f here, f of x equals 0. And so you see the slide is almost over. I will say very little about how it's actually done. I'm just claiming you can do the same thing again, to use this Newton-Kantorovich. But there are some things which are a bit different in this case. It's a bit more difficult, this example. One problem is that f, our function curly f, is translation invariant. What that means is if you have some point cloud, for example, x approx, and then you translate all the points, it just gives you the same barcode. So this is one of the invariants that this function curly f have. And you may have in your mind another invariance that it has. So this is an issue, because if your target function has these invariances, that means your linearization L has a kernel. And so this is some linear map. If this has a kernel, previously I always wrote down L inverse, and it was true, all these maps were invertible, but now this doesn't make sense anymore. If it has a kernel, you cannot invert it. So there are different ways around it. One thing you can do, I guess, maybe I don't present this in the best way possible here, but one thing you can observe is for this Newton-Kantorovich theorem, you actually don't need an inverse. You actually only need a right inverse, which you have if your linearized operator is surjective. And so having a kernel is really no issue for this. This is fine. Then you'll still have to compute some operator norm. You have to compute the operator norm of your right inverse. So for this, somehow you want to get rid of these this translation invariance. So I make it seem as if you don't need to care about what exactly the kernel is, but you kind of need to know this. So what you really would do in reality in this case is you would somehow change your problem a little bit so that it makes the kernel go away. So for example, if you want to get rid of the translational invariance, you could ask that the first point of your point cloud sits at the origin or something like this. And then there's this other invariance, there's an SO3 invariance, and maybe you can imagine some creative way how you can also fix this so that the SO3 invariance goes away. And if you do this, then your parameter space, your domain, is not 3 times L dimensional anymore, but because you did all this gauge fixing, now it's 3L minus 6 dimensional. This number 6 really doesn't matter. I'm just saying, yeah, sometimes you need to change your problem a little bit to make some invariance go away. and then L is right invertible, and you can compute its operator norm pretty similar to how you did it before. And then the rest of the proof will go through, which I haven't written down. You still need to do the 3 steps. You need to compute the approximate solution, estimate its residual, do these shenanigans with the linearized operator, and then prove the nonlinear estimate, which I claim is easy, but I haven't shown you. Very good. That's a bunch of examples. I think this is a healthy place to stop. Thank you very much for listening.